Welcome to part 1 of the linked list video. This will end our 3-part series so far of learning the basics of first object references and object structures. And then the second video we had on moving references, so your moving object reference so that we can step through and have access and manipulate different parts of a linked list structure using references. And this entire last video series that's going to be split up into different parts will be dealing with an introduction to linked lists and how to completely build them. Now, while you're doing this video, or if you're in the lectures, if you want to follow along, when we go to the actual coding components, I have uploaded, you'll see 4.4 singly linked list example. This is the beginning code that I start with, so showing the node class that's presented in the actual notes, and then the linked list class with a little bit of the code started within it. And then the rest of the methods are blank, and as we actually go through implementing them in these video series. So again, at this time, if you want, you can pause the actual video and you can go get that linked list example and get that into whatever IDE you're using. And then when we hit the coding components, you can stop and try to code it yourself or follow along coding it with me. To begin with, before we go to any other code, I've just got to start on the usual lecture slides. Okay, so linked lists and link structures, part 3, linked lists. Our rudimentary, as I said, that we've been working up to of how can we have lists that grow a little bit larger and are not of a fixed finite size like arrays. So computer science definition. In computer science, a list or sequence is an abstract data type that implements a finite ordered collection of values where the same value may occur more than once. Now, common operations that we have in a list, and that we will be kind of stepping through some of them in this video series, is adding an element. In this case, you will do examples if you're adding to the start, end, or middle of a list. Retrieving a specific element, removing an element, and what happens when you're at the start of the list, the end of the list, or in the middle if you have multiple elements. Searching for a list, which will involve using a comparator, and testing to see if a list is empty and the size of a list. So a linked list is a linear linked structure. So remember, linked structure being that we have these individual nodes, that each one has an object reference to the one that's after it, and we start the list with having an object reference that holds to the very first node in the list, and we know that the very last node in the list goes off to being null, that it doesn't reference to anything else, and they're all connected together in a linear structure. Now, motivation for this is always taking into account the advantages and disadvantages as limitations you have with these structures. Is one of the advantages that we have over arrays is that they can grow as large as memory can hold. Inserting and removing elements does not require shifting of the data because now it's just updating references between the points. And groups like information together, so still like what we had for arrays. Now for limitations, they do not provide a quick random access. So with arrays, you can give it an index and internally in the memory it can jump to that location fast. We don't have that with array lists. Since we don't have it's all different parts of memory and only the previous node linking to the next node, so we need to give it time to actually move to that spot. So to ask a specific node, you must set a moving reference that advances until we get to desired node. So it's a disadvantage, but if we have cases where we want to split apart lists, do a lot of adding, inserting at different locations, and we don't have to worry about a lot of random quick access lookups, then linked lists can be a good beginning point for a data structure to use with your algorithm. So now, there are a lot of different variations that you can create with linked structures and even linked lists themselves, and some have some classic names, but it's really more as creative as you want to get. So first, a terminology that we use in this course, and you'll see in a lot of other places, nodes in what's called a singly linked list only have a link to its successor in the sequence, so being the node that follows after it. So it always has a start reference that holds on to the list. So you always need to have that start beginning reference, your object reference, that will be used to reference the very first node in the list. and then every node after that will have a reference. It'll have its data and whatever else it's need, and then a reference to the node that follows after that. Moving references in this case begin at the start and can only move in one direction through the list. So as you expect, we don't have random access to all the rest of these nodes. We only have the first one that links to this node and a chain of them after that. So you always start your moving reference to be at the first node, and then it will step forwards in this one direction. So knowing that I get to the next. So once you have a moving reference that's out here, it can't step one back because there is no reference that has access to do that work. Now, we can modify having a singly linked list is that we could also include an end reference if we wanted to. This allows for quick access to both the start and end of the actual list. So what that means is as you're building up, you start in the beginning with a start and end reference, and you make sure as you're adding and removing nodes that the start is always going to the first node and the end is always going to the last node. Now, this would allow for speed up if you know that you're going to do adds a lot at the end of the actual list. So it would be good to have, instead of having to make a moving reference that goes all the way to the actual end, you have this end reference that you just maintain throughout the whole creation of your linked list in different methods, and making sure it follows the rule that it's always referenced in the very end one. So if you want to add to the end, you have a quick access to it at that point in time, but then you need to modify the end as you move through it. Another example is doing a circular linked list, which allows that instead of being null at the very end of the list, the last node always links back to the very first node and creates this cycle. This is useful for things called circular queues, where you have a list and you're always just continuously cycling through that list. And doubly linked lists, which are basically the same as singly linked lists, that you have a start, you could have an end reference, but what you have here is you have two links in each node. So one link that goes to the next node after it, and you have one link that goes to the previous node. And so you have two different object references in the same node. And so the next references always come to the successor that comes after them. The previous references always have to link back to the previous node that's from here. And you now have things that when you're going through the entire next, you have null at the end of the list here, and you also have null at the very beginning of the list when you've reached the start of it. But you still just have this one reference that holds onto the start, or including another end reference that includes access to the actual end of it. So example implementation. We'll be working through an example implementation of a singly linked list that only has a start reference. You can modify this in the future once you understand this code, is to add an end, which I suggest you do with working out what will be the steps required when you're drawing out everything, and then the steps you need to go back and forth. We'll be using object-oriented design combined with generics to actually do this. So what we learned very back in the beginning with the Java new and old, with the comparators and generics, will come into major play here, and why I introduced them earlier on in the course. Now, all of this code to start with is in that example code that's been provided, but to start building a linked list, you need to have some structure that holds the data and holds the actual links. So here we have an example of the node class that's generic accepting one type, so that we have the actual data type here, and we have a variable that's going to be an object reference to the next one that follows after it, since we're just doing a singly linked list. So that's why we have this right here set to null, because it's not linked into any other objects. Our constructors for setting everything up properly as we need to, so either no data or accessing the data when it's created. Our get and set methods for accessing and retrieving the actual data itself. And then the methods to set and next, since we need to manipulate and either get access to the next link or update the current link that it links to. Now to start building then the singly linked list, once we have this node, again we're doing a singly linked list without an end reference, so we need to have a starting reference. So that's why you'll see this up here as private as its first instance variable, that this is the start and it will hold the reference to the very first node. In the constructor for the class, it's called first. When the linked list is built, we have nothing in the list, so we'll set start to null to indicate that it is an empty list. Now, through the rest of the slides and breaking up partially this video and the following video, then you have the rest of the operations that we're going to go through and dealing with some of the special cases that are required in some of those operations. So first thing we need to do, in any of the operations when you're adding, removing, or moving through the list, you need to check and make sure, is the list empty or not? If it's empty, you have to react differently. So if you're adding, it means you're adding for the first time. If you're removing, well, then there's nothing to remove. If you're searching, it's a blank list, so don't search and step through. So we need a way to detect if the list is empty. And this is easy to do. That we can detect if the list is empty by checking the start reference. If the start reference is null, this means that we have nothing in the list. So that's why in the previous slide, you can see here that we set it to null to say indicating that it's empty. And we just have to always make sure if we do any removes that ends up emptying out in the entire list, so even the very first node, we also need to be careful and make sure that we update the start reference to make sure that it's null as well. So you have this example here for just doing a method now for isEmpty, becomes a very small one. So returning true or false if the list is empty or not, and all we have to do is compare start to null. So if it is null, means it's empty, and this will return true. Otherwise, it'll return false if it's linking to a node. Now to keep this method working properly, again, we just have to make sure that in our add and in our removes, we properly update start to indicate when it's null or not null, so being an empty list. Now moving on to the add element, there are 4 cases that must be dealt with when adding to a linked list. And this is your first indication when working with a lot of methods. You have to visualize what could be currently happening with the structure of the linked list at the time of running this method. So what are their different cases? And one of them you always have to deal with is the list empty? Then after that, if it's not empty, you have to worry about, well, how many nodes are there? Is there only one node? Is there 2 or 3? And how does that change how you're doing some of your work depending upon the current task? So here with add, if the list is empty, this applies, and this applies to all the other types of add that we're going to do of adding the start of the list, adding the end of the list, or adding the middle, is all of them need to check for this empty list. 2, you need to adding to the start of the list. So if we already have a node that's in there, so the list isn't empty and we're adding to the start, well, that means we're adding before the current start node, so we need to link things properly and then update the start reference so that we don't have an improper link to where the list begins. Adding to the end of the list, in this version of the list, we don't have an end reference that we're keeping, which always holds on to the last node in the list. We only have the start, so we're going to have to move through the entire list until we find the point, the last node in the list, and then link in the new one that we want. And then finally, when adding in the middle, you have to think is that if you're adding into a certain part what's in between nodes, you're going to have reference to those 2 nodes and then update the links in between them so that you have the proper chain to insert the third one in between those 2 and still preserve the linked straight structure that we are expecting. So now if we update our singly linked list class, and you already see some of these methods inside the example stuff that's given, we have the next operations that this data structure can do. So 1, adding to the start of the list, taking in the data, adding to the end the data, and then adding at a specific location. Now you'll notice for all of these that we're not accepting in a node is that for the external user on the outside of the data structure, they only care about the data. They don't care about how it's structured inside. Only the linked list itself needs to actually deal with the actual node. So here we'll just take the data and we'll make a node and put it in there and then link it in. And when they need access to anything after that, we'll just give them back the data that they want. So adding to an empty list. Very simple one to start doing. What you have to do is with the situation beforehand, what you'll assume is you've got new data, you have made a new node to store that data, and you have a reference to it, and you know its next reference is set to null. And the situation you would have is inside your linked list is that the start reference is set to null, and what you want to have happen is we want to have this done afterwards. So just that the start reference has to reference to the beginning of this node, and then we don't care what happens to the node to add after that. So really, if we know that we have the object reference node to add as only the object, we just have to make start equal to node to add. So as long as the list is empty. So if we detect that start is null, then we can just have start equal to this node and it'll hold on to the new node we've created and we're done our task. So if we go into the code, so this is in the add to start method for the class. Right here, this is the first step we do. We've got the new data. We're passing it into our new node that we want to add into the list. We check if the list is empty, which we did before, so start is null is what's being checked in this method here. Then you have start equals node to add. So you're copying that address of the new one that was made here, saved into start. And what's important is this node to add is declared locally. So when this method exits, this variable disappears, but the object that created won't, because start, which is then in your instance variables, is globally will it exist as long as the object exists for this linked list. So we're okay. So we have referenced that first node, start equals to it, and now start won't be empty. We're okay. The else that you see here is that, well, if it's not beginning of the list. So here, if we step through the code, just tracing it line by line, this first line, when it's executed completely, will create this object here, put the data in it, then the reference will be assigned into node to add, which saves here. This next check of is it's empty will return true because start is null. And then we'll go start equals new node. So node to add equals right here is referencing this object. So start will also reference this object here. Then we'll skip over the else and exit out of that method, and our list has one node that's in it. Now next, if we want to continue with this, if we're doing the add to start method, the idea is that it's always adding a node before the current node that's at the beginning of the list. So adding to the front of it. So you would have in this next situation, so if the list isn't empty, or start isn't null, what you would have is at bare minimum, you have one node or more nodes coming after this, but start will be referencing this very first node. And what we will have again is the new node with the new data that we want to add. And the idea that this has to go before this current node. And so we know this one has to link up to here, and then this has to link down to the new node. So we're going to have to go through steps of going node to add dot set next equals the current start, which goes up here, and then we're going to have to say start referencing down to here in that order. We can't go start referencing this node down here because we would have lost the first node in our actual list. We don't want to do that, so we'll link this one to the new one and make sure everything is correct first before we modify the new start. So you can see here node.add.setNext. We'll then reference this up to where you go to start first. So now we have it linking from here all the way to here. Now start is not referencing the new current beginning of the list. It's got a reference down to here. So the next line would then be to start reference down to here. So we have start to this node, and then it links off down to here, and it's doing what we expect. So it's making the new, this has been adding to the front, and start has been modified to always again be referencing the very start of the actual list. And so the end result is what we have here. Generally, this node to add will be a local reference. So once we're done from the add to start method, it'll disappear, but we'll still have start, and we'll have the entire list that we're working with. So here now going back to that add to start method, you can see, so void add to start. You can see making the new node. If it's empty, we set start equals to it. If it's not empty, it'll go into the else, where we do those steps of node.setNext, connecting to start, and then start moving to be access the new node. So this is the idea. We have a new node pointing to what should be the one that will now follow after it, and then start moves back, and it's equal to new node, so it's referencing now our new start to the actual list. And these two orders, I said this step is ordered in this way. You don't want to put start before the node to add because you would have lost the reference to the new list. We would have made this new node, and we would have lost all of the other nodes, so it's very important that that's the last step when we modify that all the changes are made, and then finally we move start back once we know we have the right structure to our list. So let's step through a couple examples now on the outside of the linked list. So assume we've created a singly linked list. It holds integers for right now, and we want to add 3 nodes to it. So in the beginning, the empty, and just adding the numbers 1, 2, and 3. So with this line of creating it, we know that in the constructor start is set to null to begin with. When we come down to here, we'll go into the add to start method. This one will create your new node and put that number 1 that's in it. Check if the list is empty. Okay, start is null, so yes, this will actually go in here. Then start will equal to this actual node right here. It'll finish, come down here, and exit out of the method. The node to add is a local variable, so it'll just disappear, and the start will still be there because it's an instance variable for the actual class. So there we go. After our first call here, we have this is the current state of the actual linked list. So our second call to add to start, we'll once again go in, make a new node, put in the data 2 here, the next will be null. Go to start is empty, which will be false, so we won't go into the if, we'll go into the else from right here. And then we have node to add dot set next. So again, not moving start, but we're updating that this will be the new node that's supposed to be at the front of the list. So its next will be what was the old start. Then start now moves to then the new start of the list for right here. And then we exit from the method. Once again, node to add is local, so it'll disappear. Start is okay because it's an instance variable and will exist as long as the object exists. And then we're left with this structure after the second call. And you can kind of see where this is going to go then for the third one. Same repeated process. So new node is created. Set to null, got data 3. It's not going to go into the if because we're coming down to here. We now have that the next here, this will go back to what is the start, which is this current one. So start's referencing here. So this next will go up to this one here. Start will then reference down to this one. And we can see that we have still proper linear structure of going into 3, going to 2, following down to 1, and then the end of the actual list. So when we come out, if I redraw this, you can see that we have, boom, the 3, 2, 1. And then the ending for the list. So that's just for adding to the front. And so again, it's just that special case of if the list is empty, you save it as the node. After that, you just make sure that you update the current node, references to the old start, and the start then moves to the proper location. So now what about if we go on to adding to the end? Now, an issue here is we're dealing with just building a singly linked list that only has a start reference, so it doesn't have an end reference. An end reference would make this easier for us, but I want to start with, bare bones, showing why you, and for end reference in a singly linked list would be very useful, but we're only going to work with one reference. And so what this means is that if we're adding to the end, we have some different situations. So first off, if the list is empty, so start is null, you're already there, it's at the end. There's only one node, so you just add it and set start equal to that. So we're fine. What we have to deal with this afterwards is that we have one or more nodes that are actually in the list. So what we need to do is we need to set a moving reference to the very beginning of the list and move all the way to the end so we find where the end is and then properly insert it from there. And so we don't have that direct reference. Now, but what we do have is we know the last node in the list, its next reference will be set to null. So what we can do is if we start the start and this start isn't null, we can look at and go through each node by node, setting it to it and say, okay, is this reference null? No. Okay, well then follow the link and go to the next one. Is this reference null? Yes. Okay, hey, look, we're at the end last node, and so once we're here, we can then now go through and start updating this. And so in this situation, again, we'd have the node that we want to add, we'd have the end reference that's right here, and we want to link everything here so that this was the old end, this would become the new end, and then preserving that we have null after that. So here, again, we're going to have to set up a moving reference that begins at the start of the list and moves forwards until the end of the list is reached. Once we reach the end of the list, we can then link the nodes together. And if we had maintained a direct link to the end of the list, we wouldn't even need this moving reference. We would have just used that end reference and linked everything in. But we would have also had to modify that every method we worked with properly updates and moves the start and end references so they keep the same situation we're always expecting of start to the beginning node, end to the last node. So let's work out the steps on the board. So drawing this out, which is the first step. Why I encourage you to do this. Most people seem to, for some reason, of not listening to me for this guidance and just jump straight into the code and not realizing you should try, if you don't know how to write the code, look at the different situations that we have, draw it out visually for the steps you'd have, step by step, and think, okay, well, how would I then translate that drawing of those steps into the actual code itself? So I will switch to OneNote. And we'll start drawing a few things out. So first situation, if we're doing the add to the end method, we have to do everything. First thing is to always check, is this the only node? Is this an empty list? If it is, we don't need to find the end because we are at the end and we just add it in there. So remember, that would be if we had our start reference right here and it was null. So you just check. So if we have start reference and if it's null, we would have our new node, we'll say right here, that we've already created to the actual object that would have the data in it, would have its next reference that's set to null, and this reference is pointing up to the new object that we've created. So if we've come in, we've got this situation that we see right here of the start reference is equal to null right here, and we have our new node that we're adding, then all you're doing after that is making your start equal to the new node you've done right here. And so it references right there, and then we're done. That's our add to the end. So if start's null, then well, there's nothing else in the list, so you just start beginning in here, and we're done at this point in time. So after the call to add end with when it's been empty, we would be left with this situation of this one node that's within here. So I'll just redraw all of this to make it a little bit smaller. So the next case is once we add, say, have one more node after this, we assume that they say right now we have one node that's in the list. So we have the data, we have the next reference right here, we have our data right here, and start is referencing this. So if we've come in and we're adding a new node again, right here, so we assume we have, we'll assume we've already now created the new object with the new data in it. It's got its next reference set to null. Have a reference to that node that we want to add. So in this situation here, we have a list that has one element in here. We have one reference we want to get to, and we want to make sure we update everything. And so we may not know exactly how many nodes we have in the list, but we know as we have the start and it's not empty. So what we need to do is now start stepping through each of these and finding out, is this null or not, and continuously doing that. So the first thing is then to set up a moving reference right here, and we want to equal it to start, so it equals to this. So again, if start's not null, we make a moving reference, and we do this in the beginning. Then we want to think is, we want to keep moving forwards and now having check, and we set this to here, and while what it's looking at is not null. Because if we find out any time that moving reference is null, if we keep moving forwards, well then moving reference has gone off the end of the list. But what you can always do is just end up going like your moving reference dot get next, like this. And what this is checking again is going M, you're going dot, which takes you up to the actual object itself. So going from M up to here, you get the get next and check this as null. And what this line would check you is if, okay, if I'm looking at that and checking to see if this thing here is null, then I know, okay, we're at the end of the list. So example, if I have this equals null, it means, okay, this is the last node and we are at the end of the list. Okay. But we want to know this is, what if there's multiple more methods? So that's fine for this one case is, yeah, this would be null, but we want to keep moving it forwards until we actually do hit the actual end of the actual list. So what we want to start with is, well, we can go like M equals your start to the list, and then we can do while M dot get next does not equal null. We can do a loop and we can keep moving forwards. So while we're a current reference, when we look at what's the next object after us is not null, keep moving forwards and keep moving that reference. So we would just go M equals get, M equals M dot get next. Okay, and so this loop here starts at the beginning, and what will happen is, okay, M dot get next does not equal null. Okay, if the next node is not null, okay, move to it. So now the moving reference will go from this to the next one, and we'll go up and check. And what will happen is this will go all the way until it detects that the next one is null, and then once we're exiting out of the bottom of this while loop, what we will know is that we will have a reference to the very end of the list. So in the case of the current situation that we are dealing with right here is if we get M equals to start, which we have here, and then we go while M dot get next does not equal null, we go up here, gets this is null, so this will go to actually being like, this will be false from right here, and we will exit out of the actual while loop, and we have a reference to the end of the list. If we have more than one node, it'll keep moving forwards. So I'll come back to this when we go to actually code this, but this is the idea of moving a reference until we get to the last node, but stopping before it exits the entire list. Okay, so let's assume now we have this situation we're adding. We've moved a reference to the end, so we have the one node here. We've moved our reference to the end, so this is the end of the list. And what we want to go through is we have our new node over here. And now, important to this one, it's not too bad. All we have to know is that making sure that our new end node right here, that its next reference is to null. Well, that's done in the new linked list. Now we have to take our old end, and well, it's now not the end one, so we have to make it equal to this node. And what we know is that this end right here, which would be the new node to add, is holding the reference to that object. So we can just go m.setNext equals that. So if we go m follow up from here to this object, does it set next, and we may assign it then to the end that we link over to here. And there we go. We're done at this time. So adding to the end is more of just moving to the end and then updating this actual end reference right here. Okay, now let's go back and actually try to code some of this. So now to code it. So you can find this if you have the add to end method in your class. We'll switch to Eclipse here. Just open this up fully. So here again, I'll just go through the class quickly. You can see again we have our start reference, your constructor that sets it to null to be empty in the beginning. Your public is empty, returns so checking if it's an empty list. We have the add method we did before. So add node to start equals new node. If it's empty, start equals the new node. So this is if the list is empty, just add at the beginning. Otherwise here, for adding to the start, new node equals our start, and our start moves back to then equals that new node. Now here's our add to end. So let's go through coding everything in this. And I will type everything else instead of copying it out. So first thing you need to know, since we're adding a new node in here, we need to take the data and move it into there, into an object. So just like we have right there. So make a new node object, putting type here, that's the generic type that's passed in. Oops. Give it some name. Pass in the data since we have a constructor to automatically assign the data. So we have our new node made. Next is we need to, before doing anything else, is the list empty? That's again, you should be always checking if you're adding, removing, or moving anything through the list. We want to check if it is empty. So this is why I made that method earlier for this one of is empty. Otherwise you check if start equals to null. If it is empty, well then your start just has to equal to your node to add, because the list is empty. So even for adding the end, if the list is empty, start, you have to add the first node, start equals there, that is the end of the list, and we are done. Otherwise, we have to go through that situation of what we drew out before, is that, well, we have the start reference, but we now need to move to the very end. So remember, going back to our drawing, is that if we're here at the actual start, we have a node here, we have to move all the way to the end till we get to the last node and then start linking everything in. So first thing to do this, we need to make a moving reference. So we don't want to change our start reference at all right now. And so we need to make a new one, node I'm just going to call this one M for right now, for being our moving node, and we make it equal to our start. So that we know if we're getting into here, there would have been at least one node in the list, so this will reference to that very first node. The next thing we need to do is move that reference all the way to the actual end of the list, since we don't have an end reference. And I said again, we can always do this now first by checking like m dot get next. And if this is null, so this is the current object we're looking at going in there. So I said, so m right here going .get next, getting the references that in here and seeing is it null or is there another one that's after that. So we want to move this to the end, so we can just keep checking, okay, well, while m.getNext does not equal null, so if it's not null, meaning there's another node afterwards, just move it forwards. So m equals m.getNext. So this is the moving forwards phase. So we check in here. If the next one is null, it's going to stop, not go into the while, continue past this here. If the actual m.getNext, so look at the next reference, is null, so it'll stop leave, but if it is not null, it'll go in and then move to that new object and loop back up and check once again. Are we at the end? No, okay, move forwards. Are we at the end? No, okay, move forwards. So what you're guaranteed then is that this line here starts as the beginning, is that this entire loop will move till we get to the very end of the list itself. And so this next line after leaving the while loop means, okay, now our m reference will be guaranteed to be at the end of the list. So we'll have the case of right there of m being at the end of the list. So now what we know is that we have a new node we want to link to. We have the current node that is the end of the list where this is null, and now this has to link over to here. So that's where we have. So we have node to add is a new one that we want to add to. We have m that's at the end. So m.setNext is equal to node to add. So going from m right here, dot set next equals over to here, which is that node to add. And as long as we've guaranteed in our node class that the next reference is set to null, we still have maintained the end marker of our actual list. So we are done the add to end at that time. That's it. There's nothing else. Start doesn't need to be modified. We've linked into the end of the list. We'll have a new one within here. This node to add is okay because it'll just disappear. It's a local variable. This m reference is a local variable, so it'll just disappear once we leave this method. But the start reference that has the entire beginning of the list and linked to all the nodes afterwards is always kept as the instance variable up here, so it exists for the lifetime of that object. So we are done our add to end, one of the smaller methods. Okay, let's for now go back and now go to the notes to the next part. So we have done the adding to the start. We have done adding to the end in dealing with this. But what about a case if you want to add to the middle? So what this means is in between two nodes. So really where you give it an index and it's going to go, and we want to add a case where, okay, this is in between two things that we're dealing with. Now, if we're dealing with a method where we just allow them to give us, say, an index in, and we assume that the first node in the list is 0, the next node is 1, then 2, then 3, all the way up to the end. So similar like an array list or an array. We have to worry about, okay, well, did they give us an index that's before the start of the list? Did they give us an index that's past the end of the list? And then once we're inserting, where is it happening? So is it supposed to be that we are adding to the start? So that indication that like, oh, you told us to add an index 0, so we're adding the beginning of the list, so we have to update the start references. What if it's at the end of the list? We need to modify that. And then what if it's in between two nodes? So situation for adding to the middle. So again, if the list is empty, then you know what to do. If it's whatever here, if the indexes are out of bounds, don't do stuff. But just imagine the situation right here is that if we're going in between two nodes, so if this is not the start, but this is anywhere within here, we have this new node that's right here. We need to redirect the references so that this object goes down to this one, and then this object goes up to this one. And we have to be careful not to lose any references that we're working with. Because right now, start holds on to this one, this next holds on to this one, and this new node holds on to this one. So if we want to keep this one, say if we update this next, but we didn't save like a reference to this object, we've lost everything that's come after this. So we have to now start having references to this one and to this one to be able to properly update all the links and not have anything lost, or to properly do the order that this new node links up to here first and then this one links down to here, and making sure that we have everything properly done. So if we are trying to add between any locations in the list, we will have to deal with some of the special cases. So again, if the location turns to be before the start node, if the location turns to be after the end node, so it's out of bounds, we need to deal with this. And then what's happening if we detect that we're at the end or versus in the middle. So at the middle, let's work out some of the steps once again on the board. So going back to OneNote, and we'll go through a couple situations. So one to think about is, first off, we're adding, and we have the new node that we want to add that's been created, that's over here, and the list is empty. So the first thing we should always check for, even if it's the middle right here, is it the empty or what are we dealing with? But right now, we're going to be dealing with, and I'll do a little bit more of this in code than the actual board, and I'll switch back and forth, is that we're given an index, and we're going in between some of the steps. So let's assume that we're just in a situation that's not one of the special cases yet, but we're just adding in between two nodes, and what are the entire steps that we need to do? So I just want to redraw some of this. And let's just assume that we have a node right here. So it's got some data. It's referencing another node that's after this, right here, that may go off to another node or not, has its data. We have our new data that we want to actually access. This is set to null, and it's got its data element. What we'll assume also right now is that we have a moving reference that now references up to here. So we have our moving reference, and it references up to this object. So you could assume that there could be some list before this, there could be some list afterwards, and what we want a situation is that we have this node here, then should go to this node, and then this node should go to this node. So here, being careful is that you don't want to update this reference to here afterwards, because right now in a situation we have a reference to this, reference to this. If we made this reference down to here, we would have lost this one because we don't have any links that are going to it. So we want to try to keep that this is the last thing we update, and we want to modify everything else afterwards. So what we can do is we want to make this node link to this one up here, and the chain to get to this we know is m right here dot get next, which will get this one, that reference link we see here. We can also pass it then into the set that's right here. So if we go like this n.setNext equals the m, like it's m.getNext, we will then move this from being null, which would reference up to here after one line of code. And then now what we can do is, well, we have something, this references to here and this references to here, so we haven't lost a chain. We have this referencing up to here, so now we can modify so this one goes down to here. We can now say m.setNext, and we can pass in the new node so that this reference goes down to here instead. So this would be like this. So you have that chain of still going in here, down, over, and then continuing, and we're good. So that's the one case if we're adding in between the two. But as I said, when we go back to dealing with stuff in the actual coding, this is going to take a little bit more. Because what we're doing is adding at a specific location. So we need to first deal with the special cases of if the list is empty, just or first off is, okay, well, like how do we get to that spot? So the index and everything else. Does this match up to what we're trying to do? Is it the index we want to get to? And then is it the type? So where's the location we want to actually add into? This is a lot of me talking, but I'll try to go slower when I talk about this, about actually inside the code. So this is meaning like, okay, I want to go up to a specific index and insert it at that spot. So what is at that spot right now would be before, and then what it linked to is supposed to be the new thing it linking into afterwards. So here, boom, we have the add to start, we have our int index, we have our data. So we want to make the new node to store the data first. Next, we want to deal with this add at. It's supposed to go up to a specific index, but this is kind of like a crazier case. We have to know, well, how many things are in the list? Can we move to it? Have they given us an index that is not within the right range? And we have to exit out and indicate that, okay, has something gone wrong? So I'm going to first deal with that case of, well, how do we know when we're at the indexes? We have nothing else in this class yet to do that with. We just have the start node equals to null. What we could do is get a moving reference and start moving it forwards and have a counter that keeps moving up. And if when it stops at the list, it's not at the right location, so we've hit the end of the list before we expect for the actual index, well then we can modify things from there. But let's say first, I'm just going to deal with the index. This is an int. They could give us a negative number. So we want to check, okay, first that the index is greater than or equal to 0. And we'll start that indexes can start at 0. So if it's greater than or equal to 0, then we know, okay, well, we have the right code. Otherwise, we have an error. And what I'm going to do here, and you're going to have to do in the future assignment, is deal with throwing an exception. Now, we're going to treat this like a major error. Just like in an array list, you give it an index out of bounds or something else. We're going to actually deal with exception handling, so throwing a new exception. To do this first, I want to indicate what things that this method could throw. And I'm just going to use the exception class, which is the root. You can go look up exception handling again. I'm just using the very top one type of exception just for right now to keep this simpler. And what we'll do is we'll go throw new exception. And we can give it a message. And we'll just say index out of bounds. Right now. Okay, so we have index out of bounds right there. And so what happens again, if this is greater than or equal to 0, it would go in and run this code. If there's an else, we hit this exception and the exception handling system kicks in. So all of the code runs, this method leaves, and it starts going up and dealing with that try-catch system. If you need a review, you can go back to your previous courses or look up exception handling to see how this works. But this is the basic step, but we're just indicating there's a major error. Whoever's calling this method actually has to deal with it at that time. Otherwise, we're going to start going into here and we're going to start dealing with the actual special cases. So what we'll do is, let's say that if they've given us index 0, so if index is equal to 0, what this means is that we want to add at the start of the list. And we already have code to do this. We don't need to rewrite this. So this is the case is if we're adding at index 0 here for right now, then okay, that's the very first one. Well, we already have our add to start method that's up to here. And so that'll handle for us adding to the very beginning list because index 0 should be the very first node, so we want to add to start. And we'll just pass in data. And since I'm doing that here, I'm just going to move this new node here so I'm not wasting the execution. Oops. Is I just want to take this one out. And I'm going to move it down to here. So if we're not adding it to here, now we'll do it. Just so that I don't create anything extra. Now that I know I'm calling my add to start. So I know that this looks a little bit weird, but I'm just saying, okay, well for indexes greater than 0, we're fine. If we're going index equal to 0, so we're adding the beginning, we'll just call our add to start. We don't need to repeat the code. That does it for us. This will also handle the case that if they're going add at 0, and it's the first time they're adding, this will then make sure, oh, if the list is empty, it'll make it to start. It'll add it to start. Otherwise, it'll move everything and update the start references for us. So we're still okay right there. Otherwise, if it's not the very beginning, well, then that means we need to move to the proper location at that time and then update it from there. So if they're giving us anything greater than that, then we now need to do the rest of our error checking. So if they give us, if we're coming into here, index equal to 0, we have the else node. We have the node to add. Then we want to check and see, okay, what is another special case we could have? So they've given us an index to add, but what if the list is empty and they've given us an index way past the range? So if we have a case that we've gone all the way down to here, so if they have, we know that the index greater than 0, but if we have the case where the list is empty, so I'm going to use our method here. So if our list is empty right now, so there's nothing in there, and we've gotten to this point, then, well, we need to indicate an error to them that you can't do that action. So again, showing the logic. If you come in here and they've given us a -1, it'll show an error. Next, if that index is equal to 0, we'll just add to the start. So if the list was empty, it just gets added at the very beginning, which is okay. Otherwise, it updates all the nodes properly. Else, if we come in here and we're going to add a new node, if the list is empty at this time, which means that they should have given us an index that's a positive number, 1 or above, that means we can't add at that spot. There's an error, and so we need to indicate to them. So we'll also then give them a new index out of bounds. So this is like adding at a... This is like doing an array list and giving an index to add at, but it's past the end of the actual size of the list. So boom, so another error. So again, going through it slowly again is that if they give us a negative index, we throw an error. If they don't give us, so they give us a positive index. If it's 0, we just add to the start. Otherwise, we're coming in here, and if they give us an index, but the list is empty, so if it's anything greater, so 1 or above, like that's the only way we would have gotten here is if it's 1 or greater. Well, the list is empty. Nope, that's an exception error. The next thing we need to do now is, well, we need to move a moving reference to the proper index and then check the conditions. Did we reach the spot we expected moving forward a number of times? Did they still give us an index that's past the end of the list and we're at a certain, we stopped earlier while doing the moving reference. So next, set up a moving reference. Your usual beginning at the start of the list. We will then now make a counter. And this will indicate the number of moves the moving reference has done. And the idea is we want to make sure that this matches to index, so that if in the end of moving the moving reference forwards, if these two numbers are the actual same, then we are good. So first, we can go through a specific number of steps. So int step equals 0. So if we're going to a specific index and we assume the first node is 0, then 1, then 2, then 3, then we're going to want to keep moving our moving reference all the way up until the number of steps. So we start, okay, if they want index 5, we're moving up 5 nodes. So like 0, 0, 0, 1, 2, 3, 4, 5. So the 6 nodes from there I meant. So if it's index 5, we're going up from 0 to 1 to 2 to 3 to 4, then 5. And so that's what we're counting from here. We can then now move the reference. So m equals m dot get next. And next what we want to check is we want to move the reference. And the idea is we'd like it that while we're done is that this should then be at the node and spot where we're supposed to actually move. But we want to be careful. And like, what if we keep moving forwards, but we've hit the end of the list before we've gone the number of required steps from right now? And we don't know the overall size of the actual list. So we want to check is, well, if m is equal to null, so that, well, we moved to the next, but then the next was null, so we've hit the end of the list, well, then something's wrong. Like we've gone past the end of the list, past the size. So if this has happened, we want to just indicate another error. We can throw another exception saying that the index is out of bounds and exits. So it's our 3 cases of if it's negative, right there. If it's 0, we start from right here. If they then give us anything from here where they give us it's an empty list and they're trying to give us a positive number, then we should exit out because we can't insert that time. After this, if it is a proper index value and the list is not empty, we'll keep moving the references forward as long as we can. So we move forwards and we check, are we at the end? No, keep moving forwards. If we reach the end before we reach the number of index we want, then this will kick in and we'll exit out. And we'll know is that if we got to right here at this line, then this is where we can finally do the add. Right here. So if we're at this case, we're back to what we expect. So before I jump ahead, because I know that's kind of weird and I've talked a lot of it, I want to go back and go to the actual screen and draw some of these out. So you can see again when I'm trying to understand the steps that's happening. So going to the code here, First off, if index is negative, that's fine to deal with. Next, if index is equal to 0, let's add to start. That's easy enough to know to. So we're adding the beginning. If the list is empty, it'll just add the node. If it's not, it adds it properly and shifts everything for us. Otherwise, then we go through and checking. So in this case, for these lines right here, where this if would kick in, is a situation where, okay, well, we have a start reference, but it's null, and you've done an add at the middle where, say, it's trying to add at spot 2, and then it has a number there for the actual data. So, well, the list is empty. So, like, we can't do anything with that, and you want us to add after 2. There aren't any 2 nodes. There's nothing here. So that's what's happening in the code here, is it's checking, okay, well, if the list is empty, throw an exception. I don't know how to deal with that. You give us an index value that's out of that actual range. Now, what would happen after this is, okay, well, what if we're doing index, and we'll just stick with this current example right here of 2. So let's say that we're trying to insert the new piece of data at index 2 right here. And let's now assume that we have the next situation that there is at least one piece of data that's in here. So this is null. You have it going right here. And you'd assume that this would be index 0. They're wanting index 2. So what would happen for the code, again going back here, is this wouldn't have gone, this is positive value, so being 2 we're okay. If index is equal to 0, nope, it's not. So we go in here, is the list empty? Nope. So we're going down to here and we're setting a new reference is equal to 0, and taking these steps forwards. I realize now I don't need this because, boom, I've already dealt with it internally in a different way, so I don't need that variable. It's cleaning it up as we check things, and we're going to go through it for a number of steps as we can. So here this would mean that we have that M moving reference equals the actual start, and then it's checking okay, and we have the variable step is set to 0. So for the first iteration of the actual loop, M equals m.getNext right here. M.equals getNext, well then, the getNext here is null, so M goes to null right here. And then if we've come down here, oh, it's gone to null, we've gone off the end of the list, then the index you gave us, because if we're going in here, this is null, we shouldn't have. If we've gone to the right index, we should be stopping at a node that's within the actual list. If we've gone off the end of the list at any point in time, then we can just exit out. So here, what that would mean is, oh, this is null, so hey, this is wrong, throw an exception and stop completely. Now let's go for a third case. So finally, where we could have everything that we actually expect from here. So let's assume that we have a couple nodes in here. Okay. So if we go that we are adding at spot 2 and we have some data we want to add in, we know that this is index 0, this is index 1, this is index 2 we want to get here. We would have gotten all the way through here. We would have started with a moving reference is referencing up to this one. Its next check is then to go into the code, and it's going to check, okay, M equals m.getNext, and then checking if it's null. And I'm just making sure I check everything here to make sure I'm not doing anything wrong. We got steps is equal to 0 in that first step of the loop right here. So we've got everything right. We've got here. We then go M equals and get next, which is referencing that one over here. So this moves up to here. That's not null, so we exit out of the bottom of the loop. Go back to the top for the if. This changes to 1. Then we do the next step of, okay, M equals get next. So this will equal up to here. M is not null. So we go down to the bottom. We increment up this by 2. We've now reached the 2 that we expected here. So a for loop leaves, and we are left with our moving reference to where we want to add. And we notice we have a very special case we need to deal with again. showing the complexity of some of these adds. It's like, oh, we wanted to add in at an index, but now this one here is then specifically, oh, we're at the end. And so we can't use what we were drawing before. Is we have to now detect, are we at the actual end of the list? And that's going to be easy again. We can check, is M referencing this null? Is its next reference next to null? Then it means, oh, we're adding a new node to the actual end of the actual list. So we want to add it in here. So we're adding it in this index. So this will be shifted back. This will go forwards from right here. So let's go back to our code. So now we'll check. So we got the moving reference moving forwards. If it's gone through and there's been no errors, we'll be actually finally doing the adds we expect. We have another special case to deal with. So if here, okay, m dot get next is equal to null, we are adding to the end of the actual list. And that one's easy to do because, you know, if we're adding at the actual end, we just have to go m dot set next and then pass in the node that we want to actually add. And we know that we're still okay at this time because when we made this object, the next reference it had was set to null. So we're okay here. So what that would mean with what we had here for steps is that we have our moving reference right here at the end of the list. We can assume that we have our new object that's set to null. We have it set to here. So we are going m dot set next is equal to the node. So this is not null anymore. This reference is down to this one, and we still have a preserved or linked list of ba 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 ba. But we're going at this at index 2 is where we're adding this in. So we're adding at the end, so this then becomes index 3. So we'll just assume our add method is we want to insert at that index and move down. Okay. Let's go back to the code. So we're inserting at that index. So we're inserting in that node, and we have to be aware that the design of this method, even though it said it adding at index 2, it means that if there's a node there, we're just going to add it afterwards and it goes to what's happened here, and this was the new end of the list, so inserted into step 3. We could have designed this differently if we know that we wanted it to replace what's at node 2, then we would have had to shift other things around from right here. Okay, what we're going to do now is the next case is, well, what if we were adding in between? So we'll do another node at adding at index 2, that's right here, but we have these two nodes. So if we had they're adding at 2, we have a moving reference coming up to here. It's not the actual end of the list. We want to insert something in between so that this shifts further down, so this becomes the new node 2. We have to do the next steps. So let's say I want to update all of these things. We've got a node right here. Next reference points to that. This one points to null, and this is the one that's at index 3. So we'd have a new node that we want to actually insert. And it's data. And so the idea from here is that we want this one to reference down to here, and then this one to reference to actually this one, and then this one still to being to reference to actually null. And so we're going to have to go through those steps that we talked about before. So finally, what seems after a long case for our code and dealing with all the special cases and why this become a little complex is saying, okay, the index greater than 0, we're fine. If it's 0, adding to the start is a special case. Then next, adding the new node. If it's an empty list, give them an error because they gave us an index that's out of bounds. Otherwise, set a moving reference to the start and keep moving it forwards until we reach the index we want, so moving it here. While we're moving forwards, if we hit the end of the list, that means that they've given us an index value that's out of range, so give them an error. And if we've finally gotten down to here, it means, okay, they've given us an index that's in the right proper spot, so we can do the add, and we just now have to check is, well, what if the index is a null at the end of the list? If it is, then just link the current reference to the new node and we're done. Otherwise, we're dealing with in between two nodes. So we have to go through those steps to make sure that we preserve what's going on. If we go back to our drawing, we know we don't want to update this reference yet because this is the one that's only here, is referencing down to here. And if we lose that, we're stuck. So we can first reference that this links to here to hold on to it. So we can go our m.getNext and set that into here. So we'll do m.getNext to get this reference, and then go our new node.setNext is equal to what we got back from that. So that will reference up to here. Now we know that we have this going, keeping a chain to here for right now. We can break this link and we haven't lost this one, but now we need to make this one reference down to here. So that would be m.setNext, boom, here to be the new node and passing in the new node. So we take this. This then references down to here, and then our indexes then are effectively updated the right way, that we would then have 3 that's inserted there, and then that would then now be at index 4. So come back down here and do the same thing, is node to add dot set next, make it reference to the new, what we expect to be after the new node. So m is currently at the node where we're adding after. So m.getting its next, passing that in. Oop, called the wrong method. So node to add dot set next, passing in m.getNext. That is then, as I said, is making this equal making this link we see right there. And now we can update so that m.setNext is equal to node to add. And this will effectively then now change so that this is referencing down here, and we have the proper link structure as we go through here. So a longer, more complex method in showing where the adds in certain cases and special cases, and then especially in the removes, can become difficult, and then also depending on how we're designing our class. Because I had this as the adding add an index from right here, is we need to worry that the user gave us a proper index, so whoever was the other coder that's using this. So check in cases of if it's like if they gave us a negative number, then indicate an error. If we're starting the list, deal with that case. If we're not just adding to the start of the list, so index equal to 0, then for anything bigger, then we check, okay, well, is it still within bounds before we do anything? Fine. Okay, then move to the right spot to add, and anytime when we're moving to that right spot, if it's out of bounds, throw an error. So if we finally get to here and we're at the right spot, we then deal with the next case. What if we end up giving as an index we're adding at the end of the list? So using the case of m.setNext to kind of probe and see, is the current node we're at, is the next one the end of the list? Or is this the current node the end of the list? If it is, then just link this one in directly. Otherwise, if we're connecting then finally where it would be between two nodes, if we're in the list, it's not the start, it's not the end, and it's all within bounds, then our new node equals the next one after the current one we're at, and our current one at this index is then linked to that actual new node, and we've preserved the linked list structure. So, woo, that's a lot. That's a lot to get to that actual point in time. So it's been about an hour and 10 minutes now, so I'm going to stop the current video for part 1, and you can go back and practice with stuff, and in the next video we'll continue on to add in these new methods, and as we add these new methods, we'll go back and maybe update and clean up some of this code now that we know a little bit more, so we don't have a lot of repeated code that we're working with. Okay. Other than that, I hope you're awesome people and continuing with this. If you need any help, always feel free to contact me or anyone else in the class.